Okay, electrochemistry looks at using the energy from a redox reaction. So you need to have that basic understanding of redox reactions. So a couple things you should be looking at here in our first example. Iron 3 chloride reacts with hydrogen sulfide. Anytime you see a bivalent metal, you should think of it going from its iron plus 3 to its iron plus 2 state. So if that's going to be happening, okay, remember, Leo the lion says GR, so gain of electrons is reduction. So we have to have something that is going to go be oxidized. So if you look at hydrogen sulfide, okay, so that has to go higher. If positive 3 is going to positive 2, that's going lower. So you should be thinking elemental sulfur. So I'm really giving you the two half reactions for this. Okay, so you're going to have 8 H2S to balance that. We're going to have 16 hydrogen ions. Okay, remember hydrogen sulfide is an acid, so that's where your source of hydrogen ions is. And 16 electrons to balance that charge. So in order to balance this, you're going to have 16 times this. So your final equation, and I know this is probably a little unconventional, is going to be 16 FeCl3, but basically looking at the parts and I'm putting it together, plus 8 H2S yields 16 FeCl2s. So again, chlorine is the spectator ion here, and 16 HCl's. So again, 16 times 3 here, 16 times 2, plus 16 times 1 is your 48 chlorines on both sides of the equation. Okay, this equation is difficult because you have three species. You have nitric acid, you have sulfuric acid, and you have mercury. Now, I did give you a little hint here. An insoluble mercury 1 compound is formed. So this really tells you mercury is going from its elemental stage, okay, to its +1 stage. Remember, that always has a 2 with it. Okay, so you're going to balance this, 2 mercuries, and okay, this is going to be oxidation because you're losing electrons. Again, Leo the lion. Leo is loss of electrons is oxidation. Okay, and anytime you see nitric acid, it's important that it's dilute. Nitric acid is a very common oxidizing agent. Okay, and it's really the nitrate part that's going to undergo this. So since it's dilute, it's going to be NO. If it's concentrated, you get NO2. You might remember that one back when we did the copper cycle lab. That brown gas was NO2. And for balancing purposes, you balance your oxygens with water. So I have 1 oxygen here, and that'll give me 2 here. That's going to give me 4 hydrogen ions. Okay, and then to balance electrons, I'm going to need 3 electrons here. Okay, and then you're going to need to multiply to get your electrons to be equivalent on both sides. So I'm going to multiply the top equation by 3, the bottom equation, I'm just going to put this 2 in the end, so there's enough space. So this is going to give me 6 mercuries. Again, I'm going to cancel my electrons. This is going to give me 8H plus 2 NO3, 3 mercury plus 1 ions. Now, we're going to put this into the original, back into a full equation, so I'll deal with this insoluble part then. This is just giving me kind of the net, a rough net, very, very rough net. Okay, 2NO and then 4H2O. Now, I've got to put this all together into my equation. So a couple things we have to look at is we get an insoluble mercury 1 compound. So you have sulfate floating around here, which is going to be what makes that a solid, and that's important that I understand that I have 3 of those. So if I have 3 sulfates on this side, I'm going to need 3 sulfuric acids on this side. Okay. Now, this is going to be the source of 6 of my hydrogens, and you'll see I have 2 NO3s here. So I'm going to have 2 nitric acids. Oops. So this other 2 is my total of my 8 hydrogens here, and my 6 mercuries. And again, order doesn't matter. I have the mercury kind of is last up there, but and then 2 nitrogen monoxides and 8 waters. So again, I should have everything balanced at this point. Again, I have my 8 hydrogens here. Okay, I have 4 oxygens here and 2 here, which is a total of 6, and 2 times 3 is my 6 there. I have my 6 mercuries. With my 6 mercuries here, my 3 SO4s, my 3 SO4s, my 2 nitrogens, so everything's balanced on that equation. So the final is 6 mercury, it's pretty messy, 2 nitric acid, 3 sulfuric acid, 3 mercury 1 sulfates, 2 nitrogen monoxides, and 4 waters as your final equation for that. Okay, the last one is the most straightforward. So you have tin, which is a bivalent metal, okay, and you have silver nitrate. So the tin obviously is going to have to be oxidized, so it's going to go from 0. It could be +2 or +4. +2 is probably more likely because of the shielding effect. And if that goes up, that means the silver has to go down, so it's going to go to its elemental form. So we're going to get tin +2 and silver metal. So this is just a basic single replacement equation. So if we look at half reactions, Sn to Sn +2, so that's your oxidation reaction, and silver is being reduced, so Ag, and an electron is going to be Ag as the element, and then I just need to double that one. And again, you probably wouldn't even need to write the half reactions to be able to balance that one, but that's going to be important for later. Okay, again, terms that we haven't had for a while: oxidizing agent, reducing agent. Remember, oxidizing agent is the substance that causes oxidation, so it's actually the substance reduced. So silver is the substance reduced, so the oxidizing agent is your silver nitrate. Tin is being oxidized, so your reducing agent is the tin. Okay, again, that's what causes oxidation to take place. So again, reviewing lots of terms. Okay, next screen is going to be the first really new thing that's going to relate to electrochemistry. Okay, the table of standard reduction potentials is on the back of your AP periodic tables. This gives the energy in volts that a particular reaction absorbs or releases. And again, these are reduction potentials, so they're all written as a reduction reaction. So again, on the written section, you'll have that periodic table available to you. So if you're not sure what reduction is, there's another place to get that definition if you think you might get those confused. I know this is pretty small, but hopefully you can get your reference value paper out, and it won't be as small for you to read. We're going to be looking at actually assigning numerical energies to this using this table. So a spontaneous reaction has a positive energy, so that's important. Okay, the larger, more positive and E standard value is, and again, that standard is like we had when we did delta H values, that the standard is at 25 degrees Celsius. The stronger the oxidizing agent, and the smaller or more negative the electron maybe is, the stronger the reducing agent. So if you change the direction of a reaction, you change the sign, so you're going to see that, and then you're going to sum the two half reactions. So what I'm going to do is look at numbers 1 and 3 as examples here. So first thing you want to do is identify your half reactions, and that's really why I started with those first. So you won't need to rewrite them. Maybe you want to make an arrow up to your previous writings. Okay, so I just rewrote them for reference. So what you're going to have to do is find this as a reduction. So you'll need to scan your list and find this reaction. Now they don't have S8 on here, they just have sulfur. The nice thing is when you change the amount of moles, it does not change what it is. So you're going to see that this one is 0.14, but since we're reversing the reaction, making it oxidation, this is going to be negative 0.14 volts. And if you find the iron one, and be careful, there's several iron ones. This is iron going from +3 to +2. That one is 0.77, and that's positive. And you don't have to write the positive, but I'm just trying to emphasize that. So when you add those two together, you get 0.63 volts as your answer, and this one would be spontaneous. Now, it doesn't ask you that, but again, just emphasizing this as a positive energy. Okay. I'm going to do number 3 underneath just because we're running out of space here. So number 3, you're looking at the two half reactions, tin going to tin +2. Again, that one's written as an oxidation, so you'll have to find this side on the chart for reduction. Okay. And that one's right there. Okay. And again, we're reversing it, so this one's going to be positive 0.14 volts. And then you're going to do the same thing for your silver reaction. So silver plus E minus. And again, you have these already written up top, so if you don't want to rewrite them here, you can just draw an arrow up to where you have them in the top part of your worksheet. So to find silver, silver going to, from its ion to its elemental form is positive 0.80 volts, and when you add that together, you get positive 0.94 volts. So again, both of these, because they're positive, are spontaneous reactions.